Welcome to the Compadre River Watershed, where this drains 115,000 square miles of diverse terrain, ranging from mountaintops that are 14,000 feet down to low valleys of 4,000 feet. The watershed is an incredible example of seeing water as the universal solvent of life. Incredible kinds of water issues surround this area. For example, there's a lot of spotty water drainage, and so we see at times that there is water, a need for water, and sometimes there's excess water. And we recognize that water in these areas is obviously in high demand. This is a desertous area, and so water dissolves and acts as a salvation sphere around ions, so dissolving electrolytes. And in fact, one of the issues that they have in this area is a high salinity, high salt content, additionally high metal ions. So water acts as a salvation, a hydration sphere around particularly those salt compounds. And depending upon the amount of water at any given time, water shortages, of course, can affect the salinity of the water. So water is absolutely the universal solvent of life, and it comprises 60 to 90% by mass of all life. So we recognize the role of water as in its role as salvating ions and polar molecules, but additionally we recognize water as being at the heart of the biology of the area. So enzymes act in response to water. Macromolecules fold in response to water. So proteins, for example, will collapse in a way that we call the hydrophobic collapse, where the center of the molecule gets away from the water by folding into its native structure. So all of life responds to water. Life is very much a water-based phenomenon. So what a better place to think about water than in this beautiful Compadre river area. This is actually the Dominguez River, and I've built my own little water molecule. There's not much you can't do in nature with some pine cones and some sticks. Our large pine cone is the central oxygen atom, bound covalently to two hydrogen atoms, and this creates a molecule that is a bent molecule. It has bent geometry, and you can see that here. Remember too that a water molecule has is a very polar molecule. Now, polarity is a result of having atoms with different electronegativities. So remember, the oxygen is a highly electronegative atom, whereas the hydrogens are less. And so we recognize that oxygen is an electron hog. It sucks in those electrons. The electrons spend more time next to oxygen. So the oxygen gets a partial negative charge. The hydrogens get a partial positive charge. And overall, this molecule gets an overall dipole moment, where it's positive on this side and negative near the oxygen. So we could represent that maybe with another blade of grass, where we have an overall dipole moment where it's positive on the top there, where the loose part of the grass is, and partially negative on the oxygen. So welcome to the world of biochemistry. Nowhere is it more important than in nature, where water is salvating the ions in these areas. And so recognize that the ions in the water would of course be very heavily attracted to the polar water molecules. So if there's a sodium cation, it's going to be very heavily attracted to the partial negative charge of the oxygen. And so we see that this will dissolve and salvate the ions in the, and you can even see in some of these areas, some of selenium is one of the things they have trouble in these waters, and so you can actually see some of the red precipitate in these areas. So nowhere do we see water being more important than in a desertous environment like the Compadre River watershed. Here, rather than showing water with pine cones and sticks, I've used ChemDraw to draw the molecule and to still see the overall dipole moment on that molecule, and to be able to draw that
recognizing the partial negative charge that exists on the more highly electronegative oxygen. Remember, the electronegativity is 3.5 versus 2.1 of the hydrogen atoms. Therefore, the electrons that are shared in a covalent bond are shared unequally, and the electrons spend more time hanging around by oxygen, giving it that overall partially negative charge on the oxygen and partially positive charge on the hydrogens. We also recognize with this drawing that there are 4 electron groups surrounding the oxygen. The electrons in the 4sp3 hybrid orbitals, pointing to the points in a box. That is, this is a tetrahedral geometry, but because we see 2 non-bonding pairs or 2 electron lone pairs, we recognize that in fact those lone pairs take up slightly more space than do the bonding pairs, and therefore where in a typical tetrahedron we would expect to see angles of 109.5, in water we see 104.5 due to the non-bonding electrons or the electron lone pairs taking up more space. Now that is also what gives this molecule its shape. So the overall dipole moment on a water molecule comes not only from the electronegativity differences in the atoms, but it also comes from the shape. Of course, a counterexample is carbon dioxide, because carbon dioxide also has a difference in electronegativity between the carbon and the oxygen. However, because this molecule is linear and not bent or V-shaped, the overall dipoles with partially negative once again on oxygen cancel one another out. So shape is everything when it comes to determining overall dipole moment. So we've looked at these sort of intramolecular interactions, that is, interactions within the molecule of water, say the covalent bond here between the oxygen and the hydrogen. But of course, water is very, very much capable of a lot of intermolecular interactions with other, say, polar or charged things like salts and whatnot. So we'll take a look now at some of those intermolecular interactions. The first intermolecular interaction that we'll take a look at is hydrogen bonding between 2 water molecules. Of course, the partially positive hydrogen atom very attracted to the partially negative oxygen atom, and that attraction, dipole-dipole interaction, is what draws these together in a hydrogen bond. Now, in a non-distorted hydrogen bond, the energy of that bond is approximately 20 kilojoules per mole. So hydrogen bonds are individually very weak, especially when we compare them to the covalent bond that this hydrogen is involved in with this oxygen. 20 times stronger at an energy of 460 kilojoules per mole. Not only is the hydrogen bond much weaker, but it's also much longer, about 2 times the length of that of a covalent bond. Now, please don't mistake that for an insignificance of hydrogen bonding within water, because individually weak, but collectively strong.
Here we are back in the Compadre water rivershed, only this time we're at 10,000 feet up on the mesa rather than being down in the bottom of a canyon. We're pondering why it is that ice floats. So you can see behind me we've got some sweet ice. It's beginning to melt as the day gets warmer. And you're thinking, wow, why is it that ice floats to the top of the water? Ice is actually phenomenal because the hydrogen bonds in ice are perfectly aligned. So rather than in liquid water where they're ephemeral and not quite aligned, in ice there's a perfect alignment of the hydrogen bonds, and that perfect alignment allows for the hexagonal lattice to form. And the hexagonal lattice has greater space in it than in the fleeting hydrogen bonds of water. So water is actually more dense than ice. Water is unlike any other molecule in that way. Typically at solids, they become more dense, but water, because of the space that's allowed by that hexagonal lattice, becomes less dense. Therefore, the life-giving feature of water that allows it to float to the top.
you'll recognize the six-fold or hexagonal symmetry of ice in the beauty of every single snowflake. And Martin Chaplin of London South Bank University teaches an entire course on the chemistry of water. Oh my gosh, get jazzed. And if you take a quick look at one of his images of water in the form of ice, where we see the regular hexagonal pack of even and very symmetric hydrogen bonding, you can of course see right away the way in which there are pockets of air leading to the lower density of ice. But have you ever zoomed in and looked really close at a single water molecule within a hexagonal packed lattice and thought to yourself, how many hydrogen bonds is each water molecule engaging with, and with what orientation? So I did that, and I suggest you do too, and draw the single water molecule and depict each one of the hydrogen bonds. Let me show you my cheesy drawing. So here central is the one water molecule that I've zoomed in on, and then looked at the fact that each hydrogen will bond with an H bond to each oxygen here, and then each oxygen can hydrogen bond to two hydrogens. So a water molecule can form 4 hydrogen bonds, and does form 4 hydrogen bonds in that hexagonal packing that we saw. And if you really look at the geometry here and you kind of draw the straight lines between each of the water molecules that this is binding to, you begin to see the tetrahedral geometry with which that single water molecule is binding to the other water molecules. This extensive hydrogen bonding within water is what gives it such a high specific heat. So if you've ever done an early morning triathlon and you jump into the water and you realize that the water is actually much warmer than the air temperature, you recognize that's due to the high specific heat of water. And of course the heat of vaporization, because in order to boil, we know water has to overcome those hydrogen bonds. We now recognize that, of course, water can engage in these dipole-dipole interactions, the hydrogen bonds between water molecules. But of course, if there are salts present within a solution, water will also interact with those and engage in ion dipole interactions. In this case, we're showing the salt potassium bromide. And of course, potassium bromide has a positively charged cation, negatively charged anion, and water is attracted to both. The partially negatively charged oxygen attracted to the cationic potassium ions. So water will form a salvation or hydration sphere around these compounds. That's why these are called electrolytes, because they will be pulled apart into their component ions when water is present. So we will see the formation of a hydration sphere around each one of the ions. I made a cartoon showing how this would happen, and I further shown once this hydration or salvation sphere has formed around each of the ions, if you then place it in the presence of 2 electrodes, positively and negatively charged, you'll watch the potassium ion, salvated ion, run to the negatively charged electrode, and the positively charged electrode will attract the bromide anion. So we're going to see that in the cartoon, and then in class we're going to do it for real. Salvation sphere moving to the electrodes.